Hi, everybody, and especially Godot and shader effects enthusiasts. After the last video, where we delved into the third dimension and created an animated shield around a 3D character, I would once again return to 2D and demonstrate how we can generate an electric discharge effect, which could serve as an obstacle in our space shooter, for example. Let's get started. To achieve the desired effect, we must first understand how a continuous curved line, which forms the basis of such structures, is generated. Let's start with a brief theory: fractal Brownian motion. There is an excellent source of information that explains this concept very clearly, and its source is called the Book of Shaders. It is freely available on the website thebookofshaders.com, and I often draw a lot of useful shader knowledge from it. If you are interested in a deeper understanding of the theory, I definitely recommend visiting this website and trying out the examples that complement each article. So, I'll summarize the fractal Brownian motion very briefly. We define a function that will serve as the foundation of our algorithm. In each iteration, we determine the value of this function and add it to the previous results. Then, we multiply certain parameters by predetermined coefficients and use them in the subsequent iterations. So, in other words, first, we will choose a function that we'll use for the iteration calculations. We can start with a simple sine wave, and later moving on to a more complex formula that resembles chaos more closely. Second, we'll define coefficients for changing amplitude, frequency, and the number of octaves or iterations. And third, we'll conduct numerous experiments and select a combination of input parameters that produces the best looking results according to our expectations, in this case, simulating an electric discharge. Let's start with the simplest code that implements this idea. So, as usual, we will create a new scene first. Right click, create new scene, and let's make it 2D and call it lightning. Okay, and I will add the color rect, which is a visual structure, and we need to define the material. That would be shader material as usual. Click it and create a new shader. It is shader this time, not a visual shader, just a plain one, and canvas item. I'll call it lightning and put it to the shaders folder. Okay, create and click to open the shader editor. So let me just enlarge this a little bit so we can observe results, and let's do it. I will define uniform parameters that we will need for a more precise adjustment of the effect. As I mentioned, fractal Brownian motion works based on changing amplitude, frequency, and the number of octaves, so we will certainly use these three parameters. In addition, I will add initial amplitude and also color for the resulting effect. Let's do it. Uniform. So let's start with the color, which is vector 3, and let's call it effect color. Type is source color, so we'll get this nice color picker in the inspector, and the initial value would be, for example, this kind of blue: 0.2, 0.3, 0.8. Okay, now let's define the number of octaves or iterations. It can be integer. Octave count, we will add it as a hint range from 1 to 20. It could be enough. And the default value is 10. Now we need the initial amplitude, uniform float this time. Let's call it amp start and start at 0 0.5. Now uniform float the coefficient to multiply the amplitude after every iteration. Amp coef is zero point 0.5. And finally, another coefficient to multiply the frequency. Frec coef, let's start at 2. Okay, so let's define the noise function. The noise function will ultimately be more complex, I would say more fractal, but for now, however, we will manage with a sine function. Since we have a vector as an input parameter, we apply the sine to the sum of its components. Let's do it. Float noise with the parameter vector to uv, coordinates of the fragment, and as I said, we will at this time return a simple result of sine sum of these x and y components. All right. The next one would be the implementation of the fractal Brownian motion. We will perform the necessary number of iterations and adjust the parameters according to the plan. Let's call the function fbm as for fractal Brownian motion. It takes uv as the input parameter and of course the number of octaves. And now the final value, let's call it value, it starts at 0 and at the end we will return it after all calculations. Okay, the amplitude starts at our initial value and start. And let's do the iterations for int I from 0 to octave count. No, octaves, sorry. Octave count is our uniform parameter. And I plus plus. And as I said, we will add a new iteration value to the previously calculated value, and it would be amplitude multiplied by result of our noise function. And now we need to change these parameters for the next iteration. So uv would be multiplied by the frequency coefficient, and the amplitude will multiply by the amp coefficient. And that's it. This is basically the implementation of the fractal Brownian motion. And finally, of course, the fragment function. As usual, we will shift the origin to the center. So let's do it this way. And this time, we'll also change the scale to -1 to +1 in both directions. So the UV would be 2.0 multiplied by the standard UV, and let's subtract 1 to make this. And now we need to add the result of this fractal Brownian motion FBM, with the parameters UV and the number of octaves, which is our uniform parameter octave count. All right. Okay, what now? Now we need to calculate the color, which will be based on the absolute value of the x-coordinate of this value uv, because we want to generate lightning from top to bottom. So let's do it here. Float this for distance would be absolute value uvx. And finally, we will aim for the brightest color inside the effect, so we'll use the inverted value, which will multiply by our input color, which means this vector 3 color would be effect color, our uniform parameter, multiplied by 1 divided by dist. And finally, let's assign this resulting color to the internal value, internal parameter color, which is vector 4. So we need to use color and 1 for alpha. Let's wait for it. Okay, we have something. So the basics would be ready. By the way, an interesting effect can be achieved if we replace the sum in the sine function with multiplication or division. Let's try it. This is something completely different, and if we divide, okay, another ornament, very nice effect, but let's stick with plus for now, because these adjustments are not crucial for the final result. Let's try to improve our lighting a bit, especially in terms of its thickness. We'll replace 1.0 here with a smaller constant to filter out unwanted visual artifacts. What if we change it to 0.1? Okay, that's better. Maybe even 0.05 would be uh, this. Sorry. Once again, here we go. This is correct. That looks better. But wouldn't it be great if such a lightning flickered a bit? Ideally, with a relatively random change in intensity. Let's add a pseudo-random function that I've used before for other fractals and apply it to our calculation using the time value. We'll name the function hash12 because it returns a one-dimensional float value but expects a two-dimensional vector as input. I will do it here in the top. So float, as I said, hash12, that takes vector 2 as the parameter and returns this. Okay, this is something I believe I copied from somewhere, but it works pretty fine, so there is no need to make it even more complicated. Sorry, fract sign modulo dot product, and finally x and vector 2. I think next time I will just copy and paste that because there's no point to write it manually in the video recording. And 3, 14, 1, 2 multiplied by 43758 point this and semicolon. Okay. And we will use this function in our fragment function right here. So instead of just using the constant, we will replace it with a linear interpolation between 0 and 0.05. This, so it would be function mix, which is equivalent to lerp in GD script. And for the weight parameter, we will use this hash function. And because we want to, as I said, flicker, we will use time to modulate the value over time. Wait for it. Okay. I hope it is visible in the video, but in reality, it is really flickering. So I guess it's time to replace the sine function with a more complex one. Where is it here? Okay, because we are creating a somewhat chaotic fractal, it is necessary to ensure that its individual parts connect seamlessly. So we need something like seamless tiles. One way to achieve this is by interpolating the edge values of such a tile, which we will do with the following code. The code I'm just going to paste here. It doesn't come from me. It's an algorithm for generating so-called parallel noise. and I found it on the website godotshaders.com in a list of useful code snippets. So this time I won't write the entire code manually, I'll just copy it here to save time and avoid the usual dose of typos. Let's do it right here. Okay, here it is. So we have, all right, what did I do wrong? Of course, replace this function. So this one we can get rid of. Now this is something completely different. Okay, so we have the function, but lightning is still quite static. As we know from many game or movie effects, electric discharges should change over time. So let's add time to the calculation. It should be right here. So UV plus time right here. This starts to look pretty cool. Certainly, it would be useful to have the option to control the speed of the lightning movement. Let's add a uniform parameter called speed and incorporate it into the code. A uniform float. Speed starts as zero point 0.5, for example, and we will just multiply the time by the speed. Okay, it seems to be slower. Great. And if we wanted to move the lightning more towards the center, it seems to be on the left side, we would do it like this. So this will stay as it is, and here we will just deduct the result from 2.0. No, sorry, multiply, of course. And finally, we will subtract 1, move it there. Perfect. How do you like it? I like it a lot. I think it's a great example of using fractal Brownian motion, and there are plenty of customization options right here in the shader parameters. So it should be no problem to add a similar effect to any scene. If you enjoyed this video, I would really appreciate every like, share, subscribe, and so on. Anyway, have a wonderful day, and I'll see you sometime next time.